Hey, what's up, guys? Chung here again. Okay, so today let's take a look at this LeetCode problem, number 490, the maze. It's a good problem, in my opinion. Okay, mm, so the problem says there's a ball in the maze with empty spaces and walls, and the ball can go through the empty spaces, either up, down, left, and right, but it won't stop rolling until hitting a wall. And when the ball stops, it could choose the next direction. So I think and the maze is consists of a 2D array here, basically where 0 means a path and uh, 1 means like a wall. So in this case, and then with this maze, it also give besides the maze itself, we also have like a start and end point. So for example, the example one here, the starting point is this, which is the 0, 4, okay? And the end point is 4, 4 here. Mm, yeah, it's 4, 4 here. And the ball, it won't stop. Sorry, it won't stop until it hits a wall. Basically, what it means that, let's say, for example, starting from here, the ball can either go left and down, right? But the ball will not stop at this moment at this place. It will stop at here. So this is that where it can stop. Okay, and but and the ball can also stop from here. So the ball can only change the direction when it stops, which means from here, it can change the directions by going back here, right? It can only go back, and from here it can go down. Okay, right? Now the ball is here. So from here there are like how many options does the ball have? It has two options, either go left or go right. Okay, and when the ball stops here, right? It can also have like another option, go up and down. Okay, and here it will go to the left until it reach the end. Okay, and then it can either go up, go down, or go right. Okay, and then here. At the end, it will hit this one. It will stop at the target, and only then we will return true here. Okay, and then there's another example here. Same thing. The starting point is the same position, but the destination is like instead of here, it's somewhere here. But in this case, even though, as you can see, even though the ball can pass through, okay, so even the ball may pass through this destination, but since it won't stop here, okay, because it won't stop. It can only stop here, and here. So that's why we return a false here. Okay. Yeah, basically that's what this problem is asking you to do. Okay. Mm, I mean, this problem it's obviously a graph. It's a traverse problem. You can either use like DFS or BFS search to do this problem, you know. So, I mean, there are like two approaches, for the basic DFS or BFS, like every time, let's say when we start from here, we add all the neighbors basically, right? We add all the neighbors to the queue, okay? And then we just keep processing it. But in this case, there's a difference. I mean, when we didn't basically, if we want to maintain like for each of the neighbors we want added. Not besides the coordinates x and y, we also need to add the current directions, right? Because let's say when we seize this node here, right? When we seize when the ball is at this node, if the direction is going down, right? And then we don't have any other options but keep going down. Okay. Basically, if on the same direction, there's like the next one is not it's not a wall. We have to go in that way, right? We have to keep going until we reach the a dead end, basically. And then yeah, so we can do that, but that will it's a bit more complicated. And then for the graph, we also need to have like a scene set, right? As a scene set to so that we won't end up stuck in the infinite loop here. So if we follow the first approach, so when we have a scene here, we have I and J, right? So instead, besides Y and J, we will be also needing to like have like direction. I have a third value here because you know the same cell could be passed from different direction. It could go from this direction, or even from this direction. Okay, right? Or from this direction. That's why besides I and J, we also need like a uh, third value to identify the unique state here. Yeah, basically that's the first approach, but there is like a better approach. So I'm gonna follow the second approach, which is I think in my opinion is better. So basically, you know, still we have a scene, right? So we have a scene set here, and we'll follow the standard uh, BFS template. We will still be storing the I and J, the two coordinates. So and the way it works is like from the current starting point, we just let the ball rolling, right? Keep rolling uh, at each directions. So and then we stop and we stop we stop the rolling until it hits a wall. So basically, when the ball like start rolling to the left, it will stop here. Okay, and when the ball start rolling to down, it will stop here. And every time when the ball stops, we check if this position is our target, right? If it's target, of course, we simply return true. If not, we add we add this position to the scene set here, and then from here onwards, we'll keep uh, rolling basically. So basically from here, because the starting point is already has been added to the scene here, right? So when we uh, so from the starting point, we have two stops here. The first one is here, the second one is here. And from here, once it stops, okay, we'll start rolling again. And at this moment, since we can only start rolling back here, okay? And yeah, this one will roll back to here. But when it stops, it sees okay, so this one this coordinate position has already been seen before. So basically, this branch will just simply stop. But here, right, when we start rolling from this moment, from this position, we can either go down or go right. Same thing. When we go right, we see okay, this position has already been seen before. So we'll come come here. Okay. Same thing when we come here, we can either go right or go left. Okay, and the ball will stop here. Okay. So when the ball stop here, it will either go up, go down, and so the next one will be here. Okay, and from here, we'll roll up to here, right, and it will roll down to here. So and then this one will go here, right? It will roll to this position, and this one will roll to here. And from here onward, you can either go up or go down. Okay. And when the ball reaches here, it will also go left or right. okay? And here is nothing, but when the ball reaches here, okay, we find our target. Then that's done, okay? So, okay, so let's try to code these things up. I mean, so they're comparing with the standard BFS or DFS, BFS or DFS, whatever. The template. The only difference is that we will keep increasing the x and y until we reach the a wall, and then we'll start from there. That's the only difference. Okay, so same thing for the DFS and the BFS. We're gonna have like define the four directions here, right? It's up, down. Actually, this is up. Okay, down, left. Okay, and right. Okay, and we'll define the boundaries first. The boundaries of the maze. Okay. Oops. And is the length of the maze 0. Okay. So and then we're gonna have like a queue or stack. I'm gonna call it stack because the sequence doesn't really matter, right? So I'm gonna do a stack here to store uh, the node we need to process, and then we have a scene dot set. Okay, right? That's the scene set. Now I'm going to add this start start 0. Okay, right? That's the starting point. Start 1 to this queue. Okay, or the stack, and the same thing for the scene. Okay, so now we just need to keep looping the stack. Okay, and then in the end we return false, right? If we haven't find if we didn't find the target. So we have current I, right, and current J equals to stack dot pop, right? So that's our current one. And so what we're doing, we are like I said, we'll try to roll on 4 directions, okay? And for direction in directions, okay? Uh, new I equals to current I, okay? New J equals to current J, okay. The reason I'm doing this is because I'm going to have a while loop here. I'm going to keep rolling it until we hit like a wall. Basically, while while the new I is in the range, okay, and the new J is also in the range, okay, and the current one is still 0. We keep rolling, right? That's the new I and new J. We keep rolling this while these conditions are met, right? Basically, the new I D0, okay, right? The new J plus D1. Basically, as long as the current new I and new J are still valid, we keep moving on, follow this direction, okay? And and when this while loop is done, okay, and then the new I and new J are out of the boundaries or are hitting a wall, okay? So that in order to find the stop point, we have to backtrack by 1. We have to move back by 1. New I D0. Okay. Okay. Right. Or you can do this, or you can do you can check this, or you can check a new I plus D0 it's not valid here, right? I mean, then while the while loop is finished, you don't have to backtrack the position by 1, but either way is fine. I'm just doing this, okay? So this is more like, I think it's easier for me to understand, so to follow basically. And we just go back 1. Now the new I and new j is a position here, right? Is the stop position. Like I said, we simply check if the new I is equal to the destination 0, and new j is equal to the destination 1, right? So if that's the case, we simply return true, right? And otherwise, right? Otherwise, if the new I and new j is not in the scene, okay? If this stopping point has not been seen before, right? Then we simply do a stack dot append. Okay, we append this new I and new j. Then we'll try to start from here. Okay, and then of course we add these things, right? We add this new position to the scene here. Okay, and in the end we simply return false. Yeah, I think that's pretty much it is. Let's try to run the code here. Okay, so the test case passed. Submit. Ah, oh, sorry. I think here. N. Yeah, success. Okay, so it's passed. Oh, there's also like maze 2 and maze 3. Maze 3, yeah. Yeah, maybe I can do that later. Yeah, but for this one, yeah. I mean, it's a little bit variation comparing with the standard BFS template. The only difference is we not all the neighbors, right? Basically, not all the neighbors are valid element to be added into the queue. It's only valid when we reach the a wall. Okay, in this case, it's this one. And once we after hitting a wall, we backtrack by 1 to find the position, right? And then we start from that position. Basically, we just essentially following what the problem is asking the ball is doing, right? The ball will go, it won't stop rolling until hitting a wall. I think that's exactly what we are doing here. We let the ball keep rolling until it hits a wall, right? And when it hits a wall, we check if that position is our target or not, right? And then if not, we'll just basically we'll add that position into the scene so that we won't process that again, right? That position again, and then we'll just go from there. Uh, yeah, cool. I think that's it for this problem. Yeah, it's a very interesting like uh, BFS search problem. I believe you can also use DFS search. Yeah, I think it shouldn't make too much difference. Oh, and oh, space and the time complexity. Right. I think so the time complexity is m and n, m times n. So the worst case scenario, we have to traverse the entire 2D maze, right? And that's the time. Space is same. Space is also like scene. It's the same as the time because we might need to, the worst case, will be storing all the elements into the scene here, which is also m times n. Okay, cool. I think that's it for this problem. Yeah, thank you so much for watching the videos, guys, and stay tuned. I'll be seeing you guys soon. Yeah, bye bye.